In the 19th century, mathematics had already advanced significantly, with tools like calculus, statistics, and non-Euclidean geometry, which was starkly different from traditional Euclidean plane geometry. Armed with these powerful mathematical instruments, classical physics had matured considerably. From Newton's classical mechanics and Maxwell's electrodynamics to thermodynamics, all had been thoroughly studied by physicists. In 1875, when Max Planck was just 17 and attending university, his mentor advised him to pursue another field instead of physics. In popular terms of that era, the edifice of physics was almost complete, and future physicists would only have to make minor corrections. This might involve refining some numerical values to more decimal places. Though this might sound humorous to us now, physicists of the time genuinely believed this, mainly because virtually every experimental phenomenon and result could be perfectly explained by the existing theories. However, even in this era of seeming perfection, Lord Kelvin, the father of thermodynamics, voiced some concerns, referring to them as two small dark clouds on the horizon of physics. In a lecture in 1900, Kelvin elaborated on these two clouds. The first was related to the speed of light and the old ether theory, which would soon be dispelled by Einstein's theory of special relativity. The second was related to the equipartition theory of specific heat, leading Planck to unlock the doors of quantum theory. One might wonder, wasn't the second dark cloud the ultraviolet catastrophe? In Kelvin's original speech, he did not specifically mention black body radiation or the ultraviolet catastrophe. However, the two are related, and since breakthroughs in black body radiation occurred first, it is often referred to as the second cloud. But what are black body radiation and the ultraviolet catastrophe? Black body radiation is a phenomenon, and the ultraviolet catastrophe refers to the inability of existing theories to explain this phenomenon, thus the term catastrophe. A black body is an object that emits light solely due to its heat, without any external light source. The radiation wavelengths include not only visible light but also invisible ones like infrared and ultraviolet. The radiation spectrum is determined solely by temperature, like a heated iron emitting red light, signifying it's not too hot, while blue signifies higher temperatures. The actual relationship between wavelength and radiation intensity had already been precisely charted by experimental physicists. During this time, experimental physicists were the primary drivers of physics. They would first observe a phenomenon, and then theoretical physicists would derive an appropriate explanation. Given the advanced state of thermodynamics and statistical physics, they initially believed that the radiation from a black body, which was essentially electromagnetic waves from oscillating electrons, could be theoretically explained. However, theoretical physicists stumbled when confronted with this challenge, as existing physics failed to fully explain black body radiation. While some theories could explain parts of the phenomenon, none could cover it entirely. The Rayleigh-Jeans formula, for example, worked for low temperatures but broke down at higher temperatures. As one approached ultraviolet wavelengths, it predicted infinite energy, which was clearly impossible. This was coined the ultraviolet catastrophe. Most physicists researching this issue were trying to use classical theories, including a 42-year-old Planck. After numerous failed attempts, Planck decided on a different approach. Could he create a mathematical formula first and figure out the physics later? Eventually, he did formulate such an equation. As it had no derivation, Planck initially published it without much fanfare, intending to later explain it physically. Fortunately, given Planck's background in thermodynamics and statistical mechanics, he found that one physical assumption could derive his formula. Light energy was not continuous but quantized in discrete packets. Each packet's energy was determined by the frequency of the light, represented by E equals h nu, where h is Planck's constant and nu is the frequency. The total energy of the light is an integer multiple of these packets. Based on thermodynamics, while high-frequency light has more energy per packet, its probability of occurrence is lower. Thus, overall radiation is limited, resolving the infinite energy problem. While Planck's explanation did indeed avoid the ultraviolet catastrophe, the introduction of this quantized energy concept was quite revolutionary. How could energy be discontinuous? Thus, after the publication of Planck's formula, it did not garner much attention. Most treated it as an alternative explanation, gave it a cursory listen, and then resumed their search for answers within classical theory. As previously mentioned, the Rayleigh-Jeans formula was formally proposed 5 years after Planck's formula, which shows how little concern there was for Planck's quantum explanation. After all, even Planck himself was puzzled by what this quantized energy really meant in physics. The first person to truly demystify this was Einstein. In the famous Annus Mirabilis of 1905, among which includes his renowned special theory of relativity, Einstein published 6 papers. One of them was on the photoelectric effect. For this paper, Einstein received the only Nobel Prize in his lifetime. However, at its initial publication, it didn't create much of a stir. So, what is the photoelectric effect? It's an experiment where when you shine light on a metal plate, electrons can sometimes be emitted from the metal. In classical terms, it's as if the energy from the electromagnetic wave was converted into the kinetic energy of the electron, which is then released. But there's an anomaly. With red light, regardless of intensity, it's tough to get the electrons out. With green light, they easily pop out, and with blue light, they not only come out but do so with high speed. According to Maxwell's theory, the energy of an electromagnetic wave only relates to its intensity, not its frequency. So as long as electrons accumulate enough energy from the light, they should be able to escape. Einstein explained this phenomenon as follows. Taking Planck's quantization into account, since light comes in packets, higher frequency light has each packet, or photon, carrying more energy. Thus, when it hits an electron, it's more likely to knock it out. If the frequency is too low, each packet contains little energy, so it can't dislodge the electron. Though Einstein's explanation was reasonable, it implied that light was redefined as particles rather than continuous waves. At that time, the entire physics community believed light was a wave, not particles. The Young's double-slit experiment had already provided solid proof, and Maxwell's equations explained nearly all electromagnetic phenomena. So it was tough for people to believe light wasn't a wave, especially since the idea of wave-particle duality wasn't around. Einstein's paper didn't receive much attention, and had Planck not been the reviewer, it might have even been rejected. Although the photoelectric effect explanation was overlooked, it's understandable since Einstein was just a clerk in the patent office at the time. However, 2 years later, when Einstein applied quantum thoughts to the solid-state heat capacity domain, the second dark cloud Lord Kelvin mentioned, he caught the attention of a thermodynamics giant, Nernst, the proponent of the third law of thermodynamics. Nernst recognized the significance of quantum theory, and subsequently, under his influence, the first Solvay conference focused on radiation and quanta. Einstein was invited and presented on the heat capacity problem. After this conference, quantum theory began to gain real traction. But it was mainly among the younger generation. Many of the older physicists, including Planck himself, couldn't accept the concept of light quanta. For many years afterward, he tried to solve the blackbody radiation problem with classical theory but never succeeded. If Planck had only slightly opened the door to quantum theory, peeking in briefly before walking away, then Einstein flung it wide open, allowing a new generation of young minds to step through. What unknowns lay beyond the door of quantum theory? Let's continue our exploration in the next segment.